Just going really hard. So I was really trying to get the best as possible. So I sat down like this. And yeah, we scrambled for the day.
Which class was it?
At 4:50.
That's the program when
That was designed. That was the algorithm one. It's been like super good because I feel like super strong. So my algorithms, some of the stuff that like I never really understood before, I can understand a lot better.
I don't know what to take next week. I just need one elective. Is there something that's oh yeah, dude, I'm taking this as a 9 course. Oh, that circuits doesn't matter to you. Yeah, I'm gonna take the circuits class as 9 course.
I was just I could give now exam. I didn't have to I wouldn't be so concerned. Slamming up like I can for 3 days. But you know, I have to, it has been called work. My schedule is not accommodating that. Figure out my schedule. No, but it's a Monday, Wednesday. Told us it was like hacking doing. Our space might have been included last year. So exactly. It's like, you know, or like the actual class. I was in class.
Yeah, I finished it. I mentioned. No, I want to do it. There you have it.
To was the first question. Did you take it with the word? Dr. And who's the week for this professor online. Critical to another field.
You made it. Let's go.
Remember, usually they'll.
Call it spring.
Do you know when we're gonna get the dates for doing that? Do you know when we're gonna get the dates for doing
Talking about the subject of problem.
Are the grades pretty young and different for the date for them?
I think that's yeah, that's going to be the thing. What the distribution is complicated, we don't know them, I think that we need to sit, but otherwise you should think.
Yeah. I just use
Oh, yeah. I agree.
pretty much at all.
Yeah, I'm trying to like, so kind of.
Okay.
Yeah.
Okay. So let us get started. Today we will be completing the reinforcement learning, the atomic version, and then find a way to slowly slide into reinforcement learning for large state spaces, which will bring us the notion of the other kind of learning. This is the generalization learning, which is the stuff that you always heard about. When you hear about machine learning, you hear about generalization learning, not the reinforcement learning. But really, they're both very much important. So we will use that as the way to get in. And then the main big topic next after this would be generalization, understanding, supervised learning, and also doing some neural networks, which is probably why you took this course. And then we will get back to other things. Yes, sir.
I can ask whether no videos to watch this weekend or.
I did not send any because, I did not send any videos to watch because it wasn't very clear since I have to introduce things. So I didn't send any, yes. Okay. I mean, this weekend is over anyway, so I guess, so any other questions? Any questions? Yes.
We're going to get into Q learning, but I noticed that you still have the T values and the R values, the reward function and the probably I forgot what it's called, but you still have those functions. So how is that different from?
That's what you want to understand today. So the thing about model-free learning, both the temporal difference learning and the Q learning, they're extremely easy algorithms, but conceptually, I mean, doing it is easy. Writing and program for them is very easy, which is good for you because you will write a Q learning agent for Pac-Man as one of your projects. Okay. On the other hand, making sure that you understand why it is working is slightly tricky, not particularly tricky, but slightly tricky. So we will get to that point specifically. Okay. Any other questions? Yes.
Do you have a date set for the midterm yet?
Not yet. Other questions? Yeah.
How much notice will you give us for the midterm?
It's pop midterm. No, I will give you notice. Yeah. Any other questions? Okay. So the general expectation is that for the midterm, the stuff until sort of end of today's class would be relevant. Okay. Because the next one is a big change in topics. But I also want you to get done with the homework. So there is a lower bound. So the RL exam, RL homework questions will be given this weekend, as I said, and the whole thing will be due next week. And so that's your lower bound as to when, after that, anytime, but before that, it can't be. Okay. Any other questions? Okay, how about this? Anyone tell me this very deep question? So you interviewed some Tempe folks, you found their average IQ to be 100. You then met another Tempe folk, another Tempe person whose IQ is 300. So now what is the new estimate of the average IQ of Tempe folks? Yeah.
How big is the sample size?
I don't know, tell me. That guy.
Higher than 100.
Higher than 100, okay, greater than 100. And then somebody else said, how big is sample size? Right? So let's just act as if, so do people see where I'm going with this? By the way, this is basically what you do in Q learning and and TD learning. I'm just trying to get you there, okay? So imagine there were n original Tempians, right? That you actually checked, interviewed, and found their average IQ to be 100. So n times 100 plus 300 by n plus 1. Would you say that's correct? Okay, that could have been written also as n by n plus 1 times 100 plus 1 by n plus 1 times 300. right? No big deal. Okay, so if you know n, this is how you will update the average. This is your GRE questions, right? If you know n, this is how you update. If you don't know n, like that other guy said, all you know is it's more than 100. How much more? Well, I basically sort of take some fraction of this new guy and add it to the old guy. In fact, you can see what is happening here is this one, it's almost can be thought of as 100 plus alpha times 300, where alpha is 1 by n plus 1. Do you see what I'm saying? So it is true that that last guy is 300, it's a huge big thing, but you don't completely change your mind. You essentially act as if only a small piece. You're basically taking a small piece of that new number, where the alpha that you put there is the learning rate. When you actually know n, it's not learning really, it's just computing the moving average as the next sample comes. But more often than not, you don't know n. You have figured out over a period of time, having lived around in Tempe, that people seem to have an average IQ of 100. How many people have you seen? I don't know. You've seen, can any of you tell exactly how many people you have seen in Tempe? Obviously not. And then suddenly you find this really smart kid in Tempe, 300 IQ apparently. So you're likely to change your estimate. But you're not ready to say, it's going from 100 to 300, or basically what you really have to assume is, well, looks like it's probably more than 100. And then you see some more Tempeans, and if you keep seeing more and more of these 300 Tempe folks, then they must have taken some IQ enhancement drug last week, and they're all basically, so now the average has really moved. Do you understand what I'm saying? Okay. This is what you will wind up having to do in model-free passive learning, which is policy evaluation, or model-free active learning, which is Q learning. In both those cases, here you know the alpha, exact alpha. In both those cases, you just take some alpha, which is a small number. That's called learning rate. And those kinds of learning, those kinds of things are called hyperparameters. Hyperparameters. If you put a very high learning rate, you're like essentially saying, whatever is the newest sample I see, that's really like what Tempe is. If you have a very small learning rate alpha, then you are basically saying, this is just an outlier. I'm sure Tempe folks are still 100. Right? Okay. And one of the interesting things is, if you keep sampling Tempe folks, suppose you don't know the number of Tempe folks you have seen, and you keep sampling Tempe folks, then you can update your average IQ. Right? You can update your average IQ by essentially take your whatever is your current estimate plus alpha times the new one. In fact, you can also write this as alpha times the difference between the old average and the new sample. Where the alpha is just the name you gave to that fudge factor. The fudge factor is the hyperparameter. We call that fudge factor learning rate. Okay. And there are some interesting properties that you have to use for learning rate, such as the learning rate, as long as it's not zero, and as long as you go forward, it keeps reducing. Asymptotically, you will always get the true average. You see what I'm saying? This is the cute case of, I don't even know how many Tempians I have seen. And I just keep seeing now onwards more and more Tempians. And what, if I start with a reasonable sized alpha and I keep reducing the alpha, and if I keep seeing infinitely many Tempians, including the same people more than once, then the average asymptotically that you compute this way will be the correct sample, correct Tempi IQ average. Now, the only difference between these, so this is what basically was shown here. So in fact, you can write this as xn plus 1 by n plus 1, xn plus 1, which is the latest entity minus the previous average. And you can now think of this 1 by n plus 1 as the alpha. You see what I'm saying? So alpha times the difference is what you are using. Except here the alpha, the learning rate is exact, because you know that number of Tempians you have seen before the next one was seen. In general, in life, you don't know. You have some estimate and things start changing. That's where moving averages are invented. You see what I'm saying? Okay. So that's what we are going to be using both in temporal difference learning and Q learning. Okay. So anyway, before go there, the story till now is basically, it's all about MDPs. In the offline case, if I know the exact, first of all, I should mention one other thing. Okay, yeah, this. Some more notational differences, just keep remembering. I kept using TSAS dash for the transition function. But the transition function really is a probability. And in fact, it is a conditional probability. It's basically saying what is the probability that if you were to do action A in state S dash, you will, I'm sorry, this is wrong. TSAS dash is nothing but, that means if you were to do action A in state S, what is the probability that you will get into S dash? That's what TSAS dash was. That was a cumbersome notation. We just used it because we called it transition function. But many a time you will actually find people using the probability notation. And in particular, the conditional probability notation. How many of you know conditional probabilities? Okay, we will talk about it again, but you're supposed to remember this from the elementary probability. P A given B is P A and B by PB. So another way of saying is, if I give you the evidence that action A was done in state S, what do you think is the probability that the next state will be S dash? That's the conditional probability. Okay, so this is another notation we'll use. In fact, I'll use it today just so that you'll get used to it. Okay, and one other piece of notation is we keep using value for MDPs, but in some cases people say utility instead of value. And utility is also the long-term value, long-term cumulative reward. That's what utility is supposed to mean. So people use these terms interchangeably. So I'm just sort of putting it out there. Okay. So anyway, so in the non-offline case MDP, if you know T are basically probability matrix, which is the transition probability, and R, then you can compute V star, Q star, pi star using value iteration or policy iteration. Similarly, if I give you a policy pi, you can compute the value of the policy using policy evaluation. This is all sort of, this is full inference, pure inference. No learning involved, essentially. Numbers are given and you are essentially plugging them to get the optimal policy or optimal value. That's what we have done for the last several classes. Then we shifted into what if, in fact, T and R are not known. And T and R are not known, then you need to, one idea, you still want to say that even when the T and R are not known, the main thing is you want to either compute V star or pi star or evaluate pi. Those are the goals of what you want to do with an MDP. Okay. So the question then is the intermediate step. So the most obvious thing, which is what you saw in that lecture that you saw on our reinforcement learning, is let's try to compute the T and R based on experience, based on basically walking around in the world. That's what the Monte Carlo simulation was doing, right? And if you compute the T and R, then you have an approximate version. You will never get the true value, true T and true R. Because if you only looked at some part of the world, then you don't necessarily know the true probabilities. You know approximate probabilities. Similarly, you certainly won't know the full reward matrix because some states may not have been visited yet by the time you stop. So using this T and R, which is these approximations, you got an approximate MDP. Then you solve it exactly using your policy iteration or value iteration. That was one type of RL. You see what I'm saying? So you are actually estimating the model in the middle. The other is don't estimate the model directly, just compute the policy or the value of the policy, which is model free, which is what we'll discuss more today. Both are equally important. You know, the model based is very useful for the agent to be able to simulate future in its head. Model free is just, I know what to do. So I just have to actually, the only way I can do it is, this is basically, as I said, model free learning is what you do for things like swimming, where you just know how to put your hands. Model-based learning, hopefully, is what you do in terms of how to live your college life, where you have a model and you can say, well, if I spend this much time on this homework, this much time on this homework, will I have any more time left for anything else? Okay? Questions? So this stuff, I hope you understood. If you have questions about this, you should ask me at some point of time. And this is what we're going to discuss today. And doing this basically is connected to computing the moving average. Right, that's what it is. Okay, so in essence, let's just do the following, the policy evaluation slowly. Okay, model-free passive learning. So basically the equation is like this, right? V pi of S is expected value that's, if I give you model-free passive learning, basically means evaluating a policy pi. I told you the policy, you just need to learn its value. Or you need to compute that value. And this you should know. I mean, even if you can't write it very quickly, you should know that this makes sense, right? This is basically one version of value of a policy. So the value of policy where we are using RSAS dash formulation. We will use RSAS dash formulation for most of the reinforcement learning. Okay, so all I'm basically saying is the pi will tell you what action to do in state S, right? And then I'm just saying for that, if I do that action in state S, then I'll get to some S dash. This S dash can be any one of the other states with different probabilities. And if I were to get to S dash, then I will get my reward for doing S pi S dash. S and pi S is an action, right? Probability, the policy of a state is an action. Policy is a function which takes states and gives actions. And then of course your gamma, which is your discount factor, times V pi of S dash. This is the recursive set of, this is a set of linear equations that basically connect value of a state to value of its neighbors. The way you would do this before is you would just write these set of linear equations, solve them. Right? But the problem is if you need to write the set of linear equations, you need this. That's the model. Which is what you did. In the passive model based case, you actually computed the probabilities. Right? Okay. So now what I want to do is really what is happening here is an expectation. It's an average. Either do people, first of all, understand that expectation of a random variable distributed according to some probability distribution P. What is that? If it is a discrete distribution, it is xp of x. Sum. If it is continuous, it is p of x, xp of x dx. Minus infinity to plus infinity. Those are expectations. Expectation is the average with respect to a particular probability distribution. Right? You do realize that. Suppose I say, basically, if I just tell you that I've seen some number of people who have 100 IQ and some number of people who have 300 IQ, then you want to know probabilities. What's the probability that you will see 100 IQ people and 300 IQ people? If it is uniform, then expectation will be 100 plus 300 by 2. If on the other hand, with 0.99 probability, I will see 100 IQ people, and only 0.01 probability, I'll see 300 IQ people, then the average is 0.99 times 100 plus 0.01 times 300. Right? So the expectation basically is average with respect to a probability distribution. Right? So this actually, V pi S is an expectation. It's an average. Right? It's an average because there is a probability distribution with respect to which you are getting these numbers. And you are taking the expectation, and that will be the V pi. So whenever you have to compute an average, you can compute it by sampling. So the idea would basically be that you will say initialize V pi S somehow. Initialize it to some zeros, for example, if you want to, or whatever number you feel like. initialize them. Right? Everybody now has a current estimate. For every state, there is an estimate of its value, which is the average that you will get if you were to do the action that you're supposed to do in that state. Then do it. Do an action. So for example, if you're in state S, and let's say basically the pi is saying you should do pi S in that state S. Let's say pi S equal to A. It's an action. So you actually do action A in state S. You actually do action A in state S. And when you do it, you'll find that you went to S dash. Here, this was all simulation. This is all in your head. Here, this really happened. S dash happened. So this is like finding a new Tempe guy with 300 IQ. So when you got S dash, basically, if you really got into S dash, then I would think that by doing action A, you got to S dash. I would say that then the target, which is like the new Tempe guy, is S by S dash times plus gamma times V pi S dash. This is the 300. Notice that even though it's a formula, it's just a number. All those numbers are known. You guys realize this. This number is known because the rewards are known. How do you know rewards, by the way? You just did this transition. So the reward washed over you. So you know it. Right? And then gamma is the discount factor. You know that. V pi S dash is the current average that you associate, current value associate with S dash. It may not be correct, but with respect to it, you will update V pi of S. You see what I'm saying? Honestly, another way of looking at this whole thing is that this is a set of linear equations, but you could have done it as an iteration. I told you that instead of equation, you can make it an iteration. So, initialize all the values and then just keep iterating. Even though it's a set of linear equations, the iterative approach also will work. Whereas for V star, iterative approach is the only thing that works because you can't solve, there are no linear equations. So essentially what I'm doing is I'm solving those iterative value iteration, sorry, policy evaluation by iterating over the policy evaluation equation. I'm doing it through experience, directly by experiencing a state. And while experiencing a state, I got a reward, and I assume that the remaining part would be gamma times V pi of S dash. That's what Bellman tells me. But originally, I thought the value of V pi, value of state S is V pi S. So the new V pi S will be set to, the new V pi S will be set to the old V pi S, which is whatever you happen to have stored in the V pi, value as the value of this state with respect to this policy, plus 1 minus alpha times, we'll call this sample. Sample minus V pi S. Do you see the connection between this and the Tempe example? Sample is a 300 IQ guy. V pi S is the original average, 100. And you're saying the new average is 100 plus alpha times 300 minus 100. Okay. Where alpha is a, sorry, 1 minus alpha times. Wait, actually, no, this should be not 1 minus alpha. alpha times sample minus V pi s. The alpha is basically learning rate. So now comes the question that this gentleman asked. Am I using R and am I using PR, probability, or not in what I'm doing? Am I using the probability directly or not in doing this? Do you see what I'm saying? Why would this work? This actually, again, these things work. Figuring out why they work requires more thought. Somebody else told you it works. The reason it works is if in fact the true probability distribution is PR, then the world will satisfy that probability distribution. So if you kept doing action A in state S, if you kept doing action A in state S, with the right set of probabilities, it will go to different states. That means, for example, let's say it turns out that if I were to do action A in state 7, I will get to state 9 with probability 0.9 and state 1 with probability 0.1. So if I were to do this action 100 times in state S, approximately 90 times I would find myself in S9. And approximately 10 times I'll find myself in S1. And each time they will be updating this. So the samples, by behaving the way they're supposed to behave, will make sure that the averages work out. Do people get this? Yeah.
So we're actually never going to make that equation with this.
No, not at all.
It's just a representation.
That's just for us to understand. So the idea is, this is what you want to compute, but you don't have the probability. But this probability is how the world behaves. If you do action A in state S, that's the probability it will behave. So you just sample the world. Do you understand what I'm saying? As long as the sampling is correct, you will be fine. As long as the sampling is unbiased, it will work out exactly what, as if you are actually using probability directly. Do you see what I'm saying? So here is another thing before going forward on that. Let me see if I can show you. We'll come back. Let's see if I can see this. Where I am. Yeah, there, that one. This is basically computing. Again, this is a really silly example of computing the average age, expected age of CSE 471 students. Expected age of CSE 471 students, right? So now if I happen to know the probability distribution of the ages for 471 students, then you can compute the expectation directly. Right? I don't even need to talk to you. If I know the probability distribution saying that, you know, people in 471 with 0.9 probability, they are, I don't know what, maybe 25, and 0.1 probability 47, then I can just multiply 0.9 by 25, 0.1 by 47, add them up, that's the expected value. That's it. I never even to talk to you. If I don't have this information, the probability is, then I need to learn it. I can learn it. Basically, I still am only interested in computing the average age of the people in the class. I don't necessarily have to learn P of A. If I decide to learn P of A, that is how the age is distributed in 471, if I decided to learn that, that's an intermediate step. If I were to learn it, then essentially I can basically ask people, a bunch of people, questions, saying, how much is your age? What's your age? What's your age? And remember those kinds of floods, like that. This kind of floods, I'll say, oh, looks like there are 8 people with 21 years of age, right? And I'll divide 8 by the total number of people I asked. And I'll say that's the probability of finding somebody in 471 with age 21. Now I have got P hat A. It's not really PA because I just asked a bunch of you. That's all. I didn't ask everybody necessarily. And then once I have that, I can then compute expectation by the formula. The alternate is to just randomly sample a bunch of you, take your ages, add them up, divided by the number of samples. That will give you the average. And the reason it works is because if I randomly sample, if 21 is the much more likely age than, let's say, 47, then when I randomly sample, I will get way more 21s than 47. So it all works out. You see what I'm saying? Again, it looks like we're making a mountain out of a molehill, but exactly the kind of question that student has. Am I still using the probabilities in doing this? No, you are not. You are letting the samples decide your computation, except the samples themselves are determined by how the probability distribution is, if you're doing the sampling correctly. Yes.
I was going to ask what num A is, but I think.
What?
I was going to ask what num A is.
What is the number of people with age A? Okay. Right? Okay, fine. So that's about, go back all the way to. Okay, so this is basically, this is called TD learning or temporal difference learning. Temporal difference learning. And interestingly enough, one of the strange things is temporal difference learning has psychological validity about how humans, at least primates, learn. They have done experiments with probes into brains and so on, right? And they can basically show that the primates actually kind of do a temporal difference learning. In essence, what they're doing is they are considering, if I'm in this state and I have a very rich neighbor, then I think, even if I thought this state was a bad state before, now I think it must be a good state because I have a very rich neighbor. Even though that rich neighbor just occurred this time, next time around it might not occur again. But it does help a little bit that at least once in your life you had a rich neighbor. So the alpha times that richness has been added to your value. You see what I'm saying? So temporal difference actually has, a psychological validity. And in fact, the guy, the Rich Sutton, basically, his claim to fame is coming up with this approach, which you can think of as doing the pretty obvious thing from a mathematics point of view, basically computing moving averages. But you can also say, well, this sort of makes sense from a biological plausibility point of view. Yes.
Just to make sure I'm clear, so the just because I noticed that v pi of s is like kind of defined a couple times. So is that top one like your initial samples? Like initial value for it, and then at the bottom when it gets updated, is that after you like?
So v pi of s is basically, this is actually all of these are assignment. In programming languages, you say x equal to x plus 1. It's not mathematical equality, right? If x equal to x plus 1, you cancel x and x, 1 equal to 0. Right? None of us, bat an eyelid because we assume x equal to x plus 1 is x is the memory cell x is assigned the previous value in that cell plus 1. That's it. That's exactly what we are doing. So you can think of this as v pi s is a memory cell. It has some value before. You take that value, replace it with this new value, which is computed from the old value. So another way of thinking about it is that you can think of this in terms of vk pi s, where kth iteration, what is the value of v pi s? Really, the iteration matters nothing, doesn't matter at all.
So is the one on top like an initial guess for it, or like
Which one? Top means what?
above like the horizontal line, the one with like the sum of the probability?
No, this one.
Yeah.
No, this is just what you would do if you had transition matrix, which you don't. That's why I got my new color. So this, you never do this. Instead, you are doing this. And you are arguing this will compute the same thing as this computes. That's the argument I just did. What you really want to do is that. What you did is this. But this actually computes that. For the reasons we discussed. Okay? Any more questions on this? Again, it's obviously a very simple thing, but you can get confused in all sorts of these different ways as to, am I really using these transition numbers or not, transition probabilities or not?
So do you determine alpha like before you do sampling?
So alpha is basically a hyperparameter. People try various different alphas.
Okay.
Actually, I'll tell you in a minute, for a Q learning, I'll tell you a little bit more about alpha. You keep using these learning rates. By the way, in most of iterative approaches, in general, there will always be these fudge factors like learning rate. And all you can say is not what the value should be, but how the value should be slowly changed. So in fact, there is this other fudge factor, by the way, which is exploration exploitation. Remember last time we talked about, with epsilon probability, with 1 minus epsilon probability, you do what the greedy policy says you should do. And with epsilon probability, you do some random action. What is epsilon? It's a hyperparameter. Once again, you know what happens if you make epsilon close to 1, which basically means you're ignoring what your greedy policy is and you're always doing random exploration. If you also know what happens epsilon equal to 0, if you set epsilon equal to 0, you are basically never exploring. You're sticking to the one greedy policy you got. Right? It should be somewhere in between. And another interesting thing is that you can also talk about whether epsilon should be the same across the lifetime of the agent or should it change? Just as should the learning rate be the same through the lifetime of the agent or should it change? It turns out the epsilon with the agent's age, epsilon should reduce because as you live long enough, hopefully your greedy policy is closer to the optimal policy. At that point of time, still acting as if it's just a random policy. I mean, it's not a good enough policy, and giving humongous weight to random actions is a waste of time. You see what I'm saying? So whenever we are doing all these things, we'll give you the alpha values. If you are playing with this, you will try different alpha values. Okay. Any other questions? Okay. So this is basically saying whatever I just said in a slide form, if you don't like that slide. Okay. Again, the reason is you're avoiding learning T or learning probability PR. And in essence, you're just computing the V pi from samples by updating the moving average. And notice that the agent experiences R, but it also has a current estimate of value of S dash. And as you keep doing this, the values will keep converging towards the true value V pi S. And then alpha is the rate. One very interesting thing is that TD does every transition it does, it tries to back propagate the value. So think of this alpha thing as I did one transition, I found a rich neighbor. So I say, wow, I have a rich neighbor, and I update my value. But the next time randomly you select that guy and you do an action, and that guy goes to an extremely poor neighbor. So, oh my God, I have a poor neighbor, my value reduces. Sometime later, your value also reduces. You see what I'm saying? So there's this issue of message passing. So you look at your neighbors, they're acting, they're jumping up and down. So you start trying to jump up and down slightly. And then those guys will see that some other neighbors have very bad value. If you do this action, you're getting into them. A neighbor is somebody you get to if you do the action that the policy tells you should do. And because they are losers, you realize that I'm also a bit of a loser. Because I can't stop the probabilities. With some probability, I'll get this bad value. And so my value should not be as optimistic as it is. It should tone it down. And the fact that I toned it down now, that message will reach this other guy a little bit. So all this will happen is after a long time, things all converge. That's all. But it's great to implement, right? Because this is like an agent with a very simple mind can still implement these kinds of things. It doesn't require Gauss-Jordan elimination built into its mind. Right? You have a question?
Yeah.
What?
So I assume that if we have a very small learning rate, it'll take a long time to convert, right?
Yeah.
If we have a substantially larger learning rate, what happens?
You keep jumping around. You keep jumping around. Basically, it's like, oh, I have a rich neighbor. Wow, I increase my value. Oh, I have a poor neighbor. I'll reduce my value. So you'll oscillate. So if you look at your value with respect to time, if you look at a particular state's value as time goes on, low alpha basically means it'll slowly come to the right value and just stay. High alpha means that it goes like that. I mean, again, whenever you have questions like this, think of the corner case. Set alpha equal to 1. I mean, alpha equal to infinity, basically, in our case. Basically, that means you give the full weight. Give the full weight to the new guy. So ignore the old average. In which case, your valuation just keeps changing.
It's a bell curve and it just keeps jumping from side to side.
No, I mean, yeah, you should think of it this way. It's the damping, this one is a damped one, the other one is an oscillating convergence. And if you keep slowly reducing alpha, then basically what you're doing is you look like this. You see what I'm saying? Any of you have any background in electrical engineering? Yeah, so electrical engineering is full of this kind of stuff. Right? Essentially, the computations are small, they're just simple updates. But then the macro behavior is quite interesting. And we are getting there essentially by doing this. Okay, fine. So you could do this. Here's an example. I mean, the numbers are not that important, but I'll show you some numbers. Suppose basically I have this particular state MDP policy thing. So they're basically A, B, C, D, E are the states. And I essentially initialize them with, let's say, their immediate rewards or something. 0, 0, 0, 8. Okay. Then I was in B here and I did an east action and I did go to C. Okay, I did go to C and then I got a -2 reward while I was doing this transition. You see what I'm saying? So then what will happen? Essentially, I have a -2 reward plus the value of B. I mean, gamma times the value of B. And I'm basically assuming gamma is 1 and alpha is half. Okay, so this will be 2 plus 0. Originally, my value was 0. -2 plus 0. Originally, my value is 0. So this will be 0 will be updated to 0 plus half times -2 plus 0. That's all you did. How hard is it to write this program? Very easy. How hard is it to figure out why it is doing the right thing? Much harder. Okay, that's basically temporal difference learning. Okay, so they do a couple more iterations. Okay. Sorry. So you did notice that after the first variation, it became -1, which is what I would do because 0 plus half times -2, which is -1. And you can check that after the second iteration, this became 3. You should check well that you got that right. Because I told you what your reward is. Each time you do a transition, you know the state and you know the reward you experienced. And the state you went to, it already says, I know my value according to my current estimate. And that will change if, in fact, you do a transition from that state to some other state. And everybody is like asynchronously updating their values. This is VPI. Okay. So next is basically we want to look at Q learning. But I want to do it again slowly and then show you the Q learning thing. So the interesting thing about Q learning is that it's even more upfront. It looks even more like there's all sorts of interesting stuff going on. So for example, if I say the Q learning is trying to do Q value iteration without using the transition function. You know, value iteration. So I'll write the Bellman for Q value iteration. Q star SA. Normally you write V star S. You'll write an equation for V star S. Now I'm writing it for Q star SA is look at that and make sure that it makes sense to you. So remember that V star has a max upfront, but Q star basically is telling you that you're doing the state action A in state S. What does Q star SA tell you? Q star SA tells you what will be the expected cumulative reward you will get if you start from S, do action A, and after that, you always do the optimal stuff. Where optimal, I don't tell you what optimal is. So if you do action A from this state and from then onwards you live optimally, what is the maximum you can expect as the cumulative reward? That's what Q star is. You can basically do it by Q star iteration. So you update, you set all Q star values to be Q star SA values to be some numbers. Remember how value iteration was done. You initialize the value function to some numbers, and then you keep doing this update. Except the only difference is this time you would, instead of just updating one value for each state, for each state, I will have K values where K is the number of actions. So in this kind of a puzzle, right? In this kind of an MDP, you have 4 actions, up, down, left, right. So for each state, you have 4 Q values. Right? So I initialize all of them to some numbers. And then what I'm going to do is I repeatedly keep updating the current evaluation of QSA, Q star SA. If I do it often enough, my hope is that Q star SA is just like V pi SA. This time Q star SAs will converge to their right Q star values. Except I'm asking for a little more this time because I'm asking for not valuation of a policy, but doing optimal action. I get to do the actions myself. One cute thing I do want you to understand is if I ever give you Q function, do you know the policy? For a given Q function, do you know the policy? This is one of the nicest things. If I tell you the value of a state, you still don't know what action to do to get that value. You have to actually do that greedy evaluation. Remember, the whole point we invented Q values was so that you don't have to do that greedy. So in fact, if I'm in this state, let's say, what action will I do? This one, because that's 0.88. How hard is that? You see what I'm saying? This idea of computing greedy policy is never there. You currently, with respect to the Q values that you have stored, every state knows what its optimal action is. This is true whether you're doing Q star iteration with the transition function or without it. It doesn't matter. It's always true. And by the way, before I just go off to the model-free part, notice that even in the Q learning, if you keep doing exactly the action that is the highest Q value, there would be exploration problem. So with 1 minus epsilon probability, you will pick the value, the max Q value. And with epsilon probability, you will pick any of them. If you do that, you're doing exploration. Agreed? Okay. So now what I'm doing basically is that I want to do this, but I don't have this. I don't want to have this. But I do realize that one of the nice things about Q is this is an expectation. So expectations can always be approximated by sampling. Averages can always be approximated by moving averages. Agreed? Okay. So what I'll do, So what I'll do is I'll actually do action A in state S. So agent does a sample action. That is, let that be, it did action A in state S. If it were to do action A in state S, it will basically feel And suppose it did, and it found itself in S dash. It's very cute. This thing is almost like the previous algorithm, except it basically is doing Q learning. You'll notice because of the max in the middle. Notice I didn't say pi of S. I don't have a policy. So I do one of the nice things about Q learning is in the policy evaluation, the agent is supposed to do only the action that it is supposed to do in that state. In Q learning, actually it can do any action. A reasonable idea is to do the greedy action. A better idea is to do epsilon greedy option. In fact, complete random will also work. It just takes longer to converge. One of the mind-bending things about Q learning is even an agent which spent its entire lifetime never exploiting what it learned, only exploring. If it lived long enough, on its deathbed, it will realize, wow, I know the optimal policy. Oh, I'm dead. It's what I'm saying. Okay. The way you do the actions doesn't wind up deciding whether or not you will get the optimal values. Each sample, basically, when you do an action in a state, you get a sample. So if you do an action A in state S and you found it yourself going to S dash, then in essence, once again, the agent feels this RSA S dash, and then it finds itself in S dash. And it knows that whatever is the value it gets from S dash must be multiplied by gamma, because you won't get the full of it. And I need to basically get the V star of S dash. Except V star of S dash is nothing but max over A dash Q star of S dash A dash. Q star of S dash. So instead of remembering just the value for that guy, I remember 4 things. I picked the maximum of them. But these are all numbers. So to get you again to understand this, suppose I was in this state. This is S, let's say, and I did action go up. I did action go up, and I actually went to this state. And in doing so, I got, let's say, whatever is I don't remember what the reward was for S. Let's say this is S, and this is S dash. So S up S dash, let's say it got a reward of minus 0.1. Plus gamma times take the maximum of the Q values currently stored in this state. What is the maximum of the Q values currently stored in this state? 0.61. This is the Tempi guy. This is the new Tempi guy in this problem. You see what I'm saying? Now notice what I'm doing is I was actually trying to recompute this 0.54 because Q of doing up action in state S. And that cell now needs to be updated with this new estimate. You guys see this? So this guy actually has 4 cells in this S. There are 4 cells, but only one of them, the one that corresponds to the action you did, that's going to be updated. Okay, how do I update? The same. So this is the sample. And I have the numerical value. So what I do is Q star SA is updated as Q star SA plus alpha times sample minus Q star SA. This looks like massive cheating, right? I mean, I'm doing Q learning here, and look at this. And this. The same thing. But that's how moving averages work. You see what I'm saying? You will think that since this is the only thing that seems to have any computation at all, Q learning better have a different form here than policy evaluation. No, that's not what happens. This is just moving average. Everything else is in the sample. You get that? Okay. Okay. That's it. That's Q learning. Q learning essentially computes optimal policy. And I actually showed you, in essence, how it works, right? So here is so basically this is like the slide showing these steps. Except in this case, this slide basically thinks of, instead of talking about Q star, it will think of K plus 1th iteration Q value in terms of Kth iterations Q value. Again, am I using the probability? No. And this looks like imposing. It's just taking each state. These numbers are known. I'm just asking you at that last minute to take the max of those numbers. And even though you're taking the max of all the numbers of S dash, you're only updating one number of S, the one corresponding to the action you did in the state S. Okay. Yes.
So will this method work no matter what you initialize the Q star values?
Yes. Right. It's the same reason. Why does it work? It works the same reason. B star. Its foundations are built piece by piece by piece. Why does Q star? Why does this thing work? This works because Q star, the green one works. And this is just doing by sampling what you're trying to do in the green one. Why does the green one work? It works because value iteration works. Why does value iteration work? Because Bellman has a contraction. That's the causality. Okay. Notice again, when I said lots and lots of people do this stuff, you go into YouTube, somebody will have some piece of code for doing Q learning. How long will this code be? Anybody can write this stuff. Understanding why it works is a lot more interesting. But to use it, if somebody else figured out that it works, you can just use it. And we use lights, we use fans, we use air conditioners without understanding how they work. And if we also don't understand how computers work, fine, we just have a computer science degree, but we also don't know how these things work. It's really a question of what level of ignorance about the world working that you care about, that you can live with, essentially. Okay. That's a tableau. So this is a little, this is basically this iterative algorithm. You actually have to write Q learning for your project. So this is the algorithm for writing that. And notice that mostly what it is doing is until convergence, sample an action, get an X state S dash, and then you get the target reward, and then the target reward plus the max of the Q values of the next state multiplied by gamma. And then you nudge your current value of QSA towards that by adding an alpha times that difference. Okay. So when you run this Q iteration, Q values, basically all these numbers will be nicely changed. Okay. Let me see if I can Okay, let me see if I can show this. Yeah.
All right, first I'm going to execute it by hand. So here's that cliff. Everything on the bottom is bad, and the exit on the right is good. So watch as I go.
Okay, so what is happening in this case is this is a little demonstration of Q-learning in action. You could do it yourself, but it's like cute. Okay, so here is again a simple grid world, and this is basically bad states. These are all zeros. I mean, these are all negative reward states. Basically, if you get into that state, you'll get it's a cliff, you're falling off. Okay, and so what it's doing is it is trying to figure out. It initialized all the Q values. Notice that for every state, there are 4 Q values. They're all initialized to 0 in the beginning. And as it does transitions, those numbers start changing. And one thing you want to see, as he talks about, and I'll put this video up again, you can see it slowly, is even after you find that your neighbor, one of your neighbors has a pretty bad value, doesn't mean you must have that bad value. Why? Because you are not forced to do the action that takes you to that neighbor. In the case of pi, I tell you what action you should do. Q-learning, there is free will. You know what I'm saying? Just because I'm walking on the Red Angel trail, I don't have to fall off the cliff because the cliff is there. It's not like there's requirement that I should do the normal thing and fall off. I should use my free will to pick the right action that doesn't kill me. So you will notice that even when there are neighbors that are there are states that have very bad neighbors, they can still have pretty high values. A value is the max of the Q values of that state. You can see that. Let's see.
All right, first I'm going to execute it by hand. So here's that cliff. Everything on the bottom is bad, and the exit on the right is good. So watch as I go. As I go, nothing really happens till I receive a non-zero reward. And as I receive the exit from here, in this case it was +10, and because my learning rate is still set to 0.5, which is not a good learning rate, it's way too high, but it's good for the demo. If I keep doing this, we'll see that as I leave here, I will learn something about what east does from this state. And you can see I update east. The other actions haven't been updated because I didn't do them. Right? If I go here, let's just do this for a while. Let's build up some information about going east. So it looks like going east is pretty good. What happens if I jump off the cliff? I learn that the fire pit is bad, and if I do it again, I learn that jumping off the cliff is bad. But I can do this all day long, and I will never learn that the start state is bad. Why? I guess the important thing here is when I move from here east, I land in a state which has some good options and some bad options. But when I do my Q update, I maximize over them. And so I only incorporate that 9.8, not the -89. So you can see that even though I am jumping off the cliff every time, in fact, the east Q values are going up because they look at the optimal thing. Okay, do that from the start here too. All right, first I'm going to execute it by hand.
Okay, I'm going to stop this. Okay, so you notice what's happening here. Just because you can die doesn't mean you must. Unless I require you, I already decided your policy, which is to take this poison. At which point you are dependent on the poison not working, to not die. Whereas if you have your free will, try not to take drugs, try not to take poison, try to take vaccine. All these things are under your control. Do you see what I'm saying? And the beauty is, of course, that all of this just works out of the box, basically, even though what you're doing essentially is a very simple moving average. And then, as I said, you also have exploration, exploitation, Q learning with probability P, pick the action with the highest Q with probability 1 minus P. In fact, I can call it epsilon. 1 minus epsilon, pick any other action randomly. I mean, I actually changed this, I guess. So I should probably call this probability epsilon. Normally epsilon is small. Epsilon, pick a random action, and 1 minus epsilon, pick the max Q value. And the last thing is that, as I mentioned, Q learning converges irrespective of how you lived. You don't need to do optimal acting to learn the optimal policy. Even if you lived randomly, if you live long enough, as I said, you will then have figured out when you are like infinity minus 25 years or so old, that, wow, I finally got the optimal policy. It's not changing anymore. And the rest of it is how to make it go faster. And normally going faster is basically greedy epsilon. And one last thing I want to say, and I'll stop here, is this rate, learning rate, which we are using in Q learning. And the thing that we basically, the theory, we are not going to go anywhere close to it right now, but the theoretically all you care about is that you can't just say learning rate becomes 0 after a point. Because an unexpected rich uncle might show up way late in your, or an unexpected really poor uncle might show up very late. I mean, I keep thinking about the fact that Jeffrey Epstein had 67 years of a beautiful life. And then he died in his cell by killing himself. That's how bad long-term rewards are. People are taking money from him because like the model citizen. So at some point of time, he stopped. If you stop learning, if alpha equal to 0 after some point, then those guys, those samples would not make any difference for you in your learning. So the sample should be such that the summation of all the alphas should diverge. So if you remember things like harmonic series, 1 plus, half plus, 1/3. Remember this series? That diverges. You do something of this kind, that's good. And the other thing is that you still want to keep the square of the alphas, that sequence, to actually converge. And it in fact turns out that 1 plus 2 square plus 3 square, that 1 by n square, that series actually converges. So that's the kind of theory you have about how to set alpha. What do people do? Programmers take some random alpha and see what happens. Do you see what I'm saying? We'll end here.
Yeah. I want to take the red.